Tell me about this
No.
uninformed person.
Hold up, let me get the marker. The problem is, we're arguing right now. And he doesn't understand, like, very basic rules, which is, like... So, the first law... somebody in the chat proposed, could you take a gyroscope, right, get it spinning, and then make that gyroscope generate electrical energy, and then have it use that electrical energy to spin itself, so it could spin forever.
Right.
And I said, no, because there's one problem. A gyroscope, it's in here, right? If it's spinning
You gotta
here...
go big. You gotta draw big. Like tiny squeeze.
So the gyroscope is in here spinning, and then it spins this way. Well, the problem is that this is creating friction here, and it's losing energy. So you can convert it from one form to the other. And he goes, well, if this other guy steps in, he goes, well, perpetual motion, isn't the universe a perpetual motion machine? I go, no, it's not. You know, you take something like a rock and you put it in space and you spin it, it'll spin forever. But if you try to convert that energy into another form of energy and then back into the other form of energy, you're always going to lose energy because of the second law of thermodynamics, which is entropy in a closed system can never decrease. It can only increase or stay the same. So the rule goes as such. If you, for example, I don't know, let's say you take a magnet or something. Or you know what, let's go with a gyroscope. You spin the gyroscope, and it's spinning really fast. Over time, it's going to slow down because as it spins, it has to spin on something, and it'll lose energy to friction, which will get radiated away as heat. So entropy is what's often referred to as disorder, and I'm just going to say it now, that entropy is not the same thing as like a government collapsing. That's chaos. That's different from entropy. Entropy is like this. So if you have, I don't know, you have a system. This will be a system. We'll go, what, like 1, 2, 3? Trying to think of a good way to...
1, 2, 3, 1, 2, 3.
Yeah, so we'll go a cube, a 9.
All right,
okay.
So 9 dots.
So the thing is or square. The thing is entropy is essentially the amount of usable energy in the system. So the idea is like you have all this energy together, all these atoms together, but over time the atoms will just kind of spread out. You know, they'll get a little more disordered, and they'll just kind of jumble themselves up. And so the idea is so like if I take a magnet and I spin it to generate electrical energy, not all of what I put into the magnet is going to be put into electricity. It's going to be, some of it's going to be lost to friction, some of it's going to be lost to electrical resistance, things like that, right? And so the idea is that basically energy spreads out. That's the main idea, right? Like right now, the sun is powering us because it has all that energy clumped up, but it's radiating away that energy. So eventually it's going to run out of energy to radiate away. And then it's going to take more energy to bring it back together and clump it all up back into a sun, right? So it's not even worth it. So the thing this guy's arguing is he's going like, okay, well, one day we'll overcome entropy. And I'm like, well, why do you think that? And he goes, well, you look at the universe is continually speeding up in expansion, which is a good argument because most physicists, we don't really understand why it's speeding up in expansion. It shouldn't, because that defies rules. But my response to that is, we don't know why it's speeding up. It could be a property of space itself. It could be scalar fields, things like that. And we don't, it could be something that'll eventually stop, or maybe it's just an inherent property of space. And then he goes, well, so then one day we'll make a computer that's so powerful that it'll be able to calculate all the atoms in the universe, and we'll be able to know the future with 100% complete certainty, which isn't a bad idea. This was proposed a while back when we thought classical mechanics was still the rule. And so it works like this. You have one atom here. If this atom is moving this way, and it hits that atom, then therefore, that atom will slow down, and this one will continue flying, right? And we can determine, if we know all the information about every other atom in the system, and we know all the rules, then therefore we can confirm the future any given point in time by just running the math forwards or backwards. Enter quantum mechanics, which makes things 10 times as complicated.
Quantum mechanics messed it up.
So I'm not gonna get too heavily into it, but basically the idea is so like in some cases in quantum mechanics, right? Like if you have a mirror here, right, and you shoot one photon, right, and this is a 50% reflector mirror, so 50% of the photons will go through, the other 50% will get reflected down. If you shoot one photon, mathematically, there is actually nothing stating whether the photon will go through here or through here. It's just a 100% complete chance, and the moment you measure it, you collapse this. This is actually called a superposition. So technically, before you measure it, it's actually in both positions, but the moment you measure it and you know where it is, it collapses the superposition. So these sorts of things pop up all the time in quantum mechanics. In fact, everything has a wave function. So this means that you can never really, like, sure, maybe if you take this computer, since everything's really big and these effects kind of get minuscule as things get bigger, if you were to take a computer, you could hypothetically calculate things like a week in advance or maybe a month, maybe even a year with like 99% accuracy. But then you start going 100 years, 1,000 years, a million years, a billion years, a trillion years, things get a little more complicated because over time these small inconsistencies are going to add up. And you'll start going from 99.9% to maybe 98, 97, all the way down to like 86, 76. Now it's shooting down to 50, etc., into the far future. So then the next problem is, even if, let's just say classical mechanics were right, and quantum mechanics didn't exist. Here's the other problem. If you wanted to scan every atom on the planet, dude, you'd have to cut the whole planet into layers. You'd have to scan every human being, every living organism on the planet, the interior of the Earth, the exterior of the Earth, every living creature, everywhere we're not supposed to be because of radioactive chemicals, every air particle. And then you have to factor in there's space, which has other particles in it.
Right.
And then the sun has its own set of particles, which you'd have to scan. Because if you don't know anything about the sun, sure, you may have the information about what will happen here on Earth in 50 years, but if a solar flare happens that knocks out all of the electricity in those 50 years, this is going to drastically change everything. So in the end, no, we cannot know the future. Entropy will always increase. Everything will die. That's
so we don't know the future because of entropy.
We don't know the future because of quantum mechanics, really.
Quantum mechanics.
I'm saying that entropy, this other argument about entropy is ridiculous, and entropy will always increase.
Okay.
That's that.
That's that.